Welcome back to Chapter 4. The last couple sections, we've been looking at the graphs of trig functions. We started out with just sine and cosine, and then we moved to tangent, cosecant, secant, and cotangent. This section is kind of the last section in that graphing piece of the trigs. It's like the next one. We're going to be looking at the graphs of composite trigonometric functions. Now, these are more of a graphing exploration thing. There are a lot of different ways these could look. We're going to look at some of the basic things to look for, but anytime you're working with this type of thing, you want to have some sort of graphing utility, whether it's a calculator or Desmos handy, partly because sometimes they do kind of weird things that you're going to want to see because it's not going to be something that's obvious, and partly because sometimes they do weird things that just flat out look cool. So it's always fun to graph some of these. You can get some pretty strange graphs. So on this, do not be afraid to have that graphing mechanism with you, because you wouldn't be expected to do it without. But again, that being said, we are going to look at a couple things that are consistent. So it'll give you some of the stuff to look for. So our learning targets, we're going to graph the composite trig functions. We're going to verify that a function is periodic and determine its period. Find the domain and range of a function. Graph the composite functions which oscillate between two lines, and determine whether a function is a sinusoid. So, first step, let's look at combining some trig functions. So I have four trig functions that are all just x squared with sine of x. We have sine of x plus x squared. We have x squared times sine of x. We have sine of x squared. And then we have sine of x squared. So all of these are a bit different. These are all going to be graphed from negative 2 pi to positive 2 pi. So that's like 2 rotations of the circle. So it should be 2 periods of sine. And then the vertical window is adjusted as needed so that we can see what it is we're looking at. And then the question here is, which of them appears to be periodic? Now, again, looking at these, you're not going to be able to just look at it and say like, oh, that one's periodic. With a little bit of practice and training, yeah, you can do a little bit, but still looking at the graph first is helpful. So here's the graphs of them. We have sine of x plus x squared. So when we add a sine function to a function, it gets it still has the shape of that function we're adding it to, but it kind of goes up and down. The quadratic here, it increases so fast that we don't even see the little fluctuations of sine. If we were adding it to just sine of x plus x, we would see, let's see, if I just graphed x, I'll do it with the black. Looks like that. So sine of x plus x would kind of look like that, like it would be oscillating kind of around that line. So we'd still see the x, it would just be kind of wavy. So this one was a, the sine of x plus x squared. So we have that x squared shape, but not quite, because the sine is just going back and forth between 1 and negative 1. The second one, we have x squared times sine of x, and that one is down here, and we only go to 2 pi. When we expand this out a bit, we're going to see a bit more, and we're going to see that later on, not specifically with this one. But later on at the end of the lesson, we'll be talking about damping factors and damping functions, and we're going to see what this kind of looks like. You can feel free to graph any of these so you can see a bigger picture of them on your calculator, on Desmos, on whatever. Again, I'm loving Desmos. It's quick and it's super easy to zoom out and change your windows and stuff. C, we have the sine of x squared. So that's just going to be the sine of x function, but we're going to square it. So notice everything's positive all of a sudden. And it's just going up down. That looks kind of like a sine function, which looks periodic because we can see the repetitions. Like there's no repetitions here. Even this one isn't, this last one, the sine of x squared, is not going to be repeating because it's getting closer and closer. The period is shortening. But this third one, C, y equals sine of x squared, is periodic. We can tell that algebraically if so we have f of x equals sine of x squared. The sine function has a period of 2 pi. So if we go x plus or minus 2 pi, doesn't really make much of a difference there, equals, and then we would replace each of the x's with x plus 2 pi squared. Well, sine of x plus 2 pi is just sine of x, so this gives us sine of x that we're still squared. If we did it to any of the others, like let's say we did it to a, we'd have f of x would equal sine of x plus x squared. Oh, and then this is back to f of x. So we moved it over 2 pi, and we're back to where we are. That's the periodicity. It's the same, it just repeats. So if we move it over, we have the same thing. Here, if we go f of x plus 2 pi, we're going to have the sine of x plus 2 pi, which will end up being just sine of x. But then we have plus x plus 2 pi squared, which is not going to simplify down to x squared. It's going to simplify to x squared plus 4 pi x plus 4 pi squared. And so that's not back to the original function. So by doing this, by replacing the x with x plus 2 pi and seeing if it will simplify back to the original function, we can tell if it's periodic or not. For the periodicity, or to find the period, sometimes it's easiest just to look at the graph and find the period. Sometimes you can do it algebraically, but looking at the graph, it's like, hey, it repeats twice for every 2 pi, so the period is now pi instead of 2 pi. Sums and differences of sinusoids. We can add sinusoids together. Now remember, a sinusoid is any function. It could be written as y equals a times sine of b times x minus h plus k. So we can write it using that sine function with transformations, or cosine function as well, because any cosine we could write as sine. And so what about when we add them together? What happens? Well, when we add them together, we might get a sinusoid. It might be that sine wave, or it might not be that sine wave. It might be something completely different. And so, how do we tell? So the sums that are sinusoids says if y1 equals a1 sine of b times x minus h1 and y2 equals a2 times cosine of b times x minus h2, then the sum equals a1 sine b x minus h1 plus a2 cosine b x minus h2. And the period is 2 pi over b. Now, there's a lot going on here. What is important? What is not important? First of all, not important is the fact that one of them is sine and one of them is cosine. They could be that way. They could both be sine. They could both be cosine. That doesn't actually make a difference. I mean, it does have to be only sines and or cosines. It can't throw tangents and stuff because that's not going to make that sinusoid, that wave pattern. What matters here is this B and this B are the same. Notice there's no subscript on the B like there is on the A. Those A values can be different. The H values can be different. There's also no K here. That complicates things a little bit when there's a K. But those B values are the same. So if we wanted to determine which of them is a sinusoid, we look. So here, the first one, we have 5 cosine x plus 3 sine x. Yep, because it's just x and x. The second one, we have cosine 5x plus sine of 3x. Those are not the same numbers, so no. Next one, we have cosine 3x and a cosine 2x. No, because those are not the same numbers. Does not matter about the number in front. We're looking at just inside the trig function has to be the same, or at least that multiplier has to be the same. Now down to the last one, we have a cosine 3x plus 7 minus b cosine of 3x over 7, b cosine 3x over 7 plus c sine 3x over 7. Hey, these are all the same. So yes, that would be a sinusoid if we graphed. I mean, the a, b, and c would have to have actual values, but it does not matter what those values are. It will be a sinusoid. It will be that wave pattern. Then how do you find the equation of that sum? Not typically algebraically, actually. To find the equation, you would graph it, and hey, it's a sinusoid. It's that sine. We've been finding the equations of that. Find your amplitude, find like all the pieces, put it into the equation. So you wouldn't go from the sum to the new equation. You'd go from the sum to the graph, and then you would approximate the equation from the graph. So there's nothing actually new there. There's nothing tricky, nothing super special. You graph it, write the equation. Now, and the period, though, will be the same. It can be, these sums can be periodic, even if they're not sinusoidal. We're going to take a look at the graph of this one, that C, the 2 cosine of 3x minus 3 cosine 2x, and see that it is actually periodic, even though it's not sinusoidal. So we take that, if we graph this, looks kind of like that. See what I mean by like zoom out, see these graphs? I mean, that's just kind of cool. Looks almost like an EKG machine, like a heart monitor. But we can see that it's periodic. It repeats itself here. Well, could we show that algebraically? Yeah, the same thing. We have f of x is this, and f of x plus 2 pi is going to be 2 times cosine of 3x plus 2 pi minus 3 cosine of 2x plus 2 pi. We can distribute that 3x plus 6 pi minus 3 cosine 2x plus 4 pi. So 6 pi is just 3 times around the circle. So 3x plus 6 pi, the cosine of that will be the same as cosine of 3x. Minus 4 pi is twice around the circle, so cosine of 2x plus 4 pi will be the same as cosine of 2x, and all of a sudden we're back to f of x. So this is periodic. Like, we can see the periodicity. We can find the period. Period looks like it's about 2 pi, because it looks like it goes from about 0 to 6. But it's not a sinusoid because it doesn't have just that basic wave pattern. Same thing, another fun one, also kind of simple, just y equals sine of 2x plus cosine 3x. What's this going to look like? Again, this is where graphing helps, because by looking at that, it's like, well, I don't know. I mean, there's so many things that could happen. That one looks kind of like this, where we get little hills, like it just kind of goes down and it has that bump in there. We could do the same thing, and they would look the same, like sine of 2 times x plus 2 pi and cosine of 3 times x plus 2 pi. We're going to have those full circles, and it is periodic. So even if it's not sinusoidal, it could still be periodic. That's how you can test it algebraically. But by looking at the graph, you should know whether you should get it to be periodic or not. And lastly, we're going to look at that dampened oscillation, that thing I mentioned at the beginning, where when we had the x squared times sine of x. And so dampened oscillation happens when we have f of x times the cosine, or f of x times the sine, when we have that function multiplied in front. So, for example, in the beginning, we had y equals x squared sine x. We'll take a look at what this is going to look like as well, even though I don't have it graphed here. I'm calling an audible, and we'll change it. So it's going to oscillate between the two functions. So if we're looking at, say, y equals x sine x, just x instead of x squared, the graph of this looks like this. Well, if I graphed this, just y equals x, y equals negative x, it is going to go right there and right there. Because as we're multiplying by sine, sine's going to go in between -1 and +1. So we're going to go in between negative x and positive x. We're never going to get outside of that. We're just going to go in between it. So that's what it's showing there. One that's perhaps a little bit more fun, y equals x squared plus 5 times cosine of 6x. If we graph this one, it looks like this. These blue dotted lines here are going to be y equals x squared plus 5 and y equals negative x squared plus 5. Those are going to be the blue dotted ones, and the cosine just goes right in between there. If we wanted to graph y equals x squared sine x, we would start out by graphing y equals x squared. Looks kind of like that. And y equals negative x squared. Don't know what just happened with my pen. That does that every once in a while. It just puts a random line. Now sine starts at 0 and goes up, and it's just going to be alternating between those lines. So that's what we would expect to see if we graphed it. Now, that graph is not labeled, it's not to scale, and it's horribly done. As you can see, you're probably looking at that thinking like, wow. All right. But this is why I usually cut and paste graphs in. I don't try and graph them myself. But that's how you can kind of do it. So what's important about the dampening here? And the dampening factor is that that function that we're looking at. It's that x, or the x squared, or the x squared plus 5. Um, what's important here, knowing that when you're multiplying a function to the sine or cosine, it's going to it's going to do this. It's going to go from the function to the negative function and just kind of go in between. And you're going to get usually some sort of a pinching. A lot of times we'll use like these, or something like e to the x, or negative e to the x, um, or e to the negative x, I'm sorry. Uh, because a lot of times it's not going to be a sinusoidal thing. A spring, you stretch a spring, it's going to go back and forth, right? It's going to go up and down, up and down, up and down, up and down. Well, eventually it's going to start slowing down. It's going to stop. That would be part of the dampening factor. So being able to recognize it, and then later on, when you get to calculus, we get something called the squeeze theorem, which actually uses this idea as well. But right now, we're not dealing with that. We're just looking at this. So use graphing. Don't try and graph by hand. Graph it. Graph everything. Play around with it. See like what happens if I do this plus this, or this times this. Sometimes it comes out to be kind of fun. Um, but do not shy away from using the graphs. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.